Greetings, gentle listeners. In this lesson, I'm going to demonstrate how to combine particles with dynamic objects. Particles can hit solid objects, and the solid objects in turn will feel the force of their impact. Here, we see the force of the particles knocking over the rather dull and featureless dominoes. And in this sequence, we can see that the particles of the liquid are being constrained by the geometry of the chutes. So let's start at the beginning. It's always a good place to start. Normally, particles and geometry do not interact. As you can see, these particles are flying straight through the ball as if it wasn't there. Maybe they're neutrinos or something. We need to do a couple of things to get the particles to collide with the ball. First, we need to make the ball into a dynamic object. So let's do that. Let's make it into a passive rigid body. This means that although it's going to participate in dynamic operations, it's not actually going to be affected by gravity and the like, so it won't fall out of the scene. Let's try running the simulation again. But still, the particles are ignoring the sphere. The next thing we need to do is to connect the particle system to the dynamic solver. So let's bring the solver into the scene so that we can see it. And we can see that it's connected to the mesh that has the sphere in it. And while we're at it, let's rename that to sphere. In order for the particle simulation and the solver to communicate with one another, we need to create a bridge between the two. And that bridge is called a dynamic collider. So if I click on that, it's added to the scene and automatically connected up to the solver and the particle simulation. Now, when we run the simulation, the particles should notice that there's a sphere there. And they do. That's a relief. There are a number of controls that affect how particles interact with surfaces. Let's look at the dynamic properties of the sphere. And under collision, you'll see a number of properties. Bounce and friction are the ones that we're interested in. With no bounce, then the particles are not really reflected from the surface at all. They just sort of slide across the surface. If we increase the bounce, then they start being reflected. And obviously the higher the bounce setting, the more vigorous the reflection will be. The other thing that we can adjust is the friction. Let's put bounce back to 0 and look at how the friction affects the particles. So with no friction they just sort of slide about, but with a lot of friction they hit the surface and stop. Somewhere in between we get a sort of intermediate behaviour. So the next thing to look at are some properties specific to the way that particles interact with surfaces. And these you'll find at the bottom here. If it's not visible, you can just click on that triangle and open up the particles section. So the roughness is a property of the reflection of the particles from the surface. So let's add a bit of bounce, otherwise we won't be able to see it in action. With 0% roughness, you can see that the particles are being pretty much reflected straight back, as though they're light particles hitting a mirror. If we increase the roughness, then the spread of the reflection increases, and we get a more diffuse reflection, as if the particles are hitting a rough surface. So in very much the same way as light particles are scattered by chalk. And obviously something in the middle gives you a slightly more directional reflection with a bit of scatter. The last property to look at is this particle collision stickiness. Now the stickiness distance controls how the particles conform to the surface after they've hit the surface. If we wind up the stickiness value and reduce the bounce somewhat, and the friction while I'm at it, we'll get there in the end. Let's get rid of the bounce entirely. Okay, finally, you can see that with a high stickiness factor, the particles hit the surface and then conform to the surface as they slide across it. We can increase the friction and they will not slide so far. So with a combination of the roughness, the stickiness, the bounce and the friction, you can configure the behaviour of the collisions in a number of interesting ways. In this next scene, I'm going to use particles to influence dynamic objects. Here I have a pair of balls on a table. But enough of my strange habits. This time, the table is already set up as a passive rigid body, but I need to make the balls into active rigid bodies because they're going to move around. So I've already got them selected. We need to go into Dynamics and select Active Rigid Body. And let's not forget that we need to connect the particle system to the solver, otherwise the particles and the objects won't know anything about each other. So let's go into Particles, Dynamic Collider, and it's automatically connected up with the scene. Now when we run the simulation, the particles should hit the balls and we'll see what happens. Well, something's happening, but it's happening awfully slowly. We need to give the particles a bit more punch. So there's a couple of ways of doing this. Just as in the real world, the effect that the collisions have will depend on the velocity of the particles and on their mass. So one thing we can do is increase the velocity of the particles. And we can do that by adjusting the settings in the emitter. So let's wind up the velocity. And the balls are being bashed a bit more vigorously. But it may be that you don't want to change the velocity. Let's put that back to something more manageable. The other way is to adjust the mass of the particles. And the easiest way to do that is to use a particle operator. Here I have a particle operator set up to set the mass to a given value, and the particle operator is configured as a new mode operator, which means that when the particles are created, the mass will be set to the value that's being fed into here. The final act is to connect the operator into the particle simulation, and now we can fiddle with the mass of the particles. Oh look! In this last example, I'm going to use the collision event feature of the particle operator to detect when a particle collides with an object. You can use this, for example, to kill the particle when it collides with the object, or you can use it to trigger a collector emitter to create a particle. In this example, I've used these features to create a raindrop-like effect. When the particles hit the surface, they are killed, they generate a new particle, which is then used as an emission source for a splash effect. It's very similar to the fireworks example that we saw earlier in the series. Let me walk you through the schematic. I've color-coded the objects in the schematic according to which simulation they belong to. So the red boxes are the source of the initial particles. These are the raindrops falling from the sky. The green boxes are those that hold the intermediate particle that marks the position of the collision, and the blue boxes are the simulation that controls the splashing particles. Let's just run the simulation and see what happens. So you can see there's a red rain falling down, as Peter Gabriel would say. That's following the same colours as the boxes. So the red rain falls down and is converted on collision into a green point, and then we have the blue splash from the final part of the simulation. So let's just have a look at a little bit more detail so you can see what's going on. We have the source of the particles, which is a simple radial emitter. They get fed into the simulation. Let me open up the connections. And we have several things connected to the simulation. We have the collider, which is just the bridge between the simulation and the dynamic solver. And we have a couple of particle operators. We have the falling impact capture operator. What this is doing is it's looking for a collision event. When the collision event is asserted, it triggers the emitter in the green section to emit a particle. The collision event is just one of the features available in the particle operators. So we capture the position of the particle, x, y and z collision position, and we feed them into the collector emitter in the green simulation part. Additionally, we have another particle operator which again is looking for a collision event. When that collision event is asserted, it simply kills the particle. Now this is where order of operations is important. We have to make sure that the killing particle operator happens after the impact detection operator. If we do these the other way around, then the particle gets killed before it has a chance to signal to the emitter that particles should be created. We also have to make sure that the collider, the dynamic collider, is before both of these particle operators. If you place it afterwards, then these collision events are not asserted at the right time and nothing useful happens. Okay, so the rest of the system is very similar to the fireworks example. We have a particle created in this green particle system. It's just created with zero velocity at the position of the collision. And it doesn't really do anything very much apart from sit around for a while. So we've turned cull by age on, and this particle will live for just 5 cycles and then get killed off. During that time, though, it will feed into this source emitter in the blue simulation section. So the particle will sit around here, but it will be used as the source of emission for this emitter. This will emit a number of particles over those 5 cycles, and then finally we need to make sure that when those particles have been emitted, gone up a bit and then fallen back to the ground, that they're killed when they hit the ground again. So again we've created a particle operator which is monitoring the collision event, and when we get a collision we kill off the particles. As a useful side effect, this means that any particles that are emitted into the ground by this source emitter will be killed straight away because they'll collide straight away. Another way round that problem is to make sure that the velocity of the emitted particles is always upwards so that they go away from the surface, but it's not actually necessary in this case. Finally, we must make sure that we have the dynamic collider connecting the simulation to the solver, otherwise we won't get any of these collisions. So that's the whole thing. Splashes from falling red rain. Oh, and one last thing before you go anywhere, I'm not sure I've shown you this. If you want to select multiple objects in the schematic, you can right mouse click and drag to drag out a marquee and select multiple objects in one fell swoop. Well, I hope this tutorial was useful, and I hope to see you next time.